Welcome to Understand the Math. Before you begin, be sure to check out the video description below for a link to free guided notes that you can download and fill in as you watch this video. This is the sixth part of a 7-part series on topics that commonly appear on an introductory linear algebra midterm or final exam. This video goes over 6 topics related to eigenvalues and eigenvectors. Let's begin with an introduction to eigenvalues and eigenvectors. We'll first look at an example where we're given a matrix A and 3 vectors. We're going to compare the length and direction of each vector to the length and direction of our matrix times each vector. Let's start with A times X. It's equal to 1, 2, 1, 0 times 1, 1, and that gives us 2, 2. A times x2 is our matrix A, times x2, which is 1 minus 1, and that gives us 0, 2. Our last one is A times x3, and that's equal to our vector A, times x3, which is minus 1, 2, and we get 1 minus 2. Let's now plot x1, x2, and x3 along with these 3 vectors that we just calculated. We'll plot x1, x2, and x3 first. x1 is 1, 1. And looks like this. x2 is 1 minus 1 and looks like this. Our last one is x3. It's equal to minus 1, 2, and it looks like this. Let's now plot ax1, ax2, and ax3. ax1 is equal to 2, 2. So it looks like this. ax2 is equal to 0, 2. And we'll plot that here. And then lastly, ax3 is 1 minus 2. And that looks like this. Let's notice that x1 and ax1 have different lengths but point in the same direction. x2 and ax2 have different lengths and they have different directions. And ax3 and x3 have the same length but point in opposite directions. I've summarized this on our next page. ax1 and x1 have different lengths but the same direction. From our calculation, we found that ax1 is equal to 2 times x1. So we can think of this as a multiple of x1. ax2 and x2 have different lengths and different directions. So we're going to say that ax2 is not equal to x2, or a multiple of it. Lastly, ax3 and x3 have the same length but opposite direction. So we say that ax3 is equal to minus x3, and that also is a multiple of x3. We'll return to this after we define what an eigenvalue and an eigenvector is. An eigenvector is a non-zero vector, that's very important, that when multiplied by a matrix produces a scalar multiple of itself. It also changes at most by a scalar factor when a transformation such as a multiplication by A is applied to it. If A is an n by n matrix and X is a non-zero vector in Rn, we can say that X is an eigenvector of A if A times X is equal to lambda X for some scalar lambda. So that's the definition of our eigenvector. And then we would say that lambda is an eigenvalue of X. So if AX is equal to lambda X, and lambda is a scalar, then X is an eigenvector, and lambda is an eigenvalue. Let's go back up to the top of the page and let's see what this means for our x1, x2, and x3. Since ax1 is equal to a multiple of x1, we say that x1 is an eigenvector of A, and 2 is our corresponding eigenvalue. For x2, it is not an eigenvector because it is not a multiple of ax2. So we'll write down ax2 is not an eigenvector of A. And then x3, just like x1, it is an eigenvector of A. And -1 is our corresponding eigenvalue. Let's head down to the bottom of our page now, and let's do an example where we need to determine if x is equal to 1, 2 is an eigenvector of this matrix A. And if it is, we need to find out what's the corresponding eigenvalue. We'll start by multiplying A times x. So A times x is equal to 3, 8, 0, minus 1 times 1, 2. And that gives us a 3 and then a 6. And we notice that 3, 6 is a multiple of 1, 2. So that tells us that x is an eigenvector of A. So we'll write down yes. And the corresponding eigenvalue is that scalar right there. So our eigenvalue is lambda is equal to 3. What's going on physically is that multiplication by A has stretched our vector x by a factor of 3. We'll now go over a procedure for finding the eigenvalues of a matrix. We know that lambda is an eigenvalue of matrix A if AX is equal to lambda x and x is not equal to 0. Let's start with A times x is equal to lambda x. And let's come up with an equation for finding the eigenvalue. Let's move everything over to the left-hand side. So we have A times x minus lambda x is equal to 0. We'll then pull out our A and our lambda. So this is A minus, now we can't just pull out a scalar because we have a matrix on our left. So we're going to pull out lambda times I times our vector x is equal to 0. To make things easier, let's let A minus lambda I equal B. So this gives us b times x is equal to 0. Since by definition, x cannot equal 0, our equation b times x is equal to 0 must have a non-trivial solution. This then tells us that the determinant of b has to equal 0 because we cannot have a unique solution. That then tells us that determinant, plugging back in for b, a minus lambda I, must also be equal to 0. And that's the equation that we're going to use to find our eigenvalues. This leads us to the following theorem. Our theorem says if A is an n by n matrix, then lambda is an eigenvalue of A if and only if, and here's where we're going to plug in that new equation, determinant A minus lambda I is equal to 0. There is a name for that equation, and it's called the characteristic equation. So the characteristic equation of A is determinant A minus lambda I is equal to 0. And if we take away the equal and the 0, we get what's called our characteristic polynomial. So that's just equal to the determinant A minus lambda I. We'll now do an example where we're asked to find the characteristic polynomial, characteristic equation, and eigenvalues of A. We'll begin by finding A minus lambda I. Let's write down A, 3, 8, 0, minus 1, and then we subtract off lambda times our identity matrix. And that gives us 3 minus lambda, 8, 0, minus 1 minus lambda. So going forward, you can probably skip that step and then just know that you have to subtract off lambda off the main diagonal. Let's now compute our determinant. So our determinant, A minus lambda I, is the determinant of 3 minus lambda, 0, and then 8 minus 1 minus lambda. And our determinant is then 3 minus lambda times minus 1 minus lambda. And that is equal to lambda squared. Looks like we have a minus 3 and a plus 1, so minus 2 lambda minus 3. Our characteristic polynomial is going to be lambda squared minus 2 lambda minus 3. Our characteristic equation is going to be lambda squared minus 2 lambda minus 3 is equal to 0. And then our eigenvalues, they are obtained by setting this expression equal to 0. So that gives us 3 minus lambda minus 1 minus lambda is equal to 0. So lambda is equal to 3 and lambda is equal to minus 1. So our eigenvalues, our lambda is 3 and lambda is minus 1. If you're finding this video helpful, please give it a thumbs up and drop a comment below. Now that we know how to find eigenvalues, we're going to learn how to find eigenvectors and a basis for an eigenspace. Since we already know what an eigenvector is, let's start by learning what an eigenspace is. The eigenspace of a matrix is similar to the null space of a matrix. Let's remind ourselves what the null space is. A null space of a matrix A is all solutions x to AX is equal to 0. The eigenspace of a matrix A corresponding to an eigenvalue lambda is all solutions to, instead of A, we're going to have A minus lambda I times X is equal to 0. Let's make a note that our eigenspace contains the 0 vector. That's always a point of confusion for students because an eigenvector cannot be 0, but an eigenspace can contain the 0 vector. So it contains the 0 vector and all eigenvectors corresponding to lambda. Let's now look at a procedure for finding eigenvectors and basis for eigenspaces. X is an eigenvector corresponding to eigenvalue lambda if A minus lambda I times X is equal to 0. Note that this is just another way of saying A times X is equal to lambda X. To find our eigenvector X, we will reduce A minus lambda I augmented with 0 to reduced echelon form. Let's now do an example where we're given a matrix and asked to find an eigenvector and basis for the eigenspace corresponding to an eigenvalue equal to 3. We'll begin with the augmented matrix, A minus lambda I augmented with 0, and then we'll plug in what that is. Our lambda is equal to 3, so we have a 3 minus 3, 8, 0, minus 1 minus 3, augmented with 0. Let's simplify that. So this is 0, 8, 0, minus 4, 0, 0. Now we're going to reduce that to reduced echelon form. So we can do two things at once. Let's switch the rows and let's divide our bottom row by 8. So this is going to give us a 1 minus a half on top because we switched the rows, and our 0 row now goes to the bottom. We have one pivot, and that's going to enable us to solve for x1. So we say that x1 is equal to 1/2 x2, and x2 is our free variable. This gives us a solution. X is equal to x1, x2, and that's going to be an x2 times a 1/2, 1. x2 can take on any value from minus infinity to infinity, so we have an infinite number of eigenvectors. To find just one eigenvector, we will choose a value for x2. I always try to choose the value that's going to make things more simple. So in this case, let's choose x2 to be 2. So the fraction's going to go away. So one eigenvector is going to be 2 times 1/2, which is going to be 1. And then 2 times 1 is 2. So one eigenvector is equal to 1, 2. Our basis for our eigenspace is going to contain this eigenvector. Before we learn about diagonalization, we need to talk briefly about similar matrices. If A and B are n by n matrices, then B is similar to A if there is an invertible matrix P, let's underline that, such that B is equal to P inverse times A times P. We say that A is similar to B if B is similar to A. Let's now define what A is equal to. We'll begin with our definition for B. So B is equal to P inverse AP, and we want to find A. So let's multiply on the left by P. So P times B. P times P inverse is our identity, so we don't even need to write that down. So that then gives us A times P. Now to solve for A, let's multiply on the right by P inverse. So that gives us P inverse is equal to A. To summarize, we say that A and B are similar to each other if A is equal to P inverse, and then likewise B is equal to P inverse AP. We're going to use that when we study diagonalization. Let's talk a little bit more about P. P is called a similarity matrix or a change of basis matrix. Similar matrices have a lot of the same properties. I've listed some of them here. It's very important to note that if two matrices are similar, they will have, for instance, the same determinant. However, if two matrices have the same determinant, they may or may not be similar. Let's do an example where we're asked to show that A and B are not similar matrices. Let's underline that. We can show this a lot of different ways by looking at the properties and calculating those properties for each matrix. I think the determinant is probably the easiest. So let's find the determinant of each of these matrices. The determinant of A is going to be 16 plus 2, which is 18. And the determinant of B is going to be 16 minus 2, which is 14. So the determinant of A is not equal to the determinant of B, so that tells us that A and B are not similar. Our next topic is on diagonalization. I remember the first time I taught this, I could not say that word correctly. I just got tongue-tied when I tried to say it. One reason for diagonalizing a matrix is that it makes it easier to analyze transformations, such as T of X is equal to A times X, or T of V is equal to A times V. Also, powers of A can be computed more efficiently if A is diagonalized. We say that a matrix A is diagonalizable if there exists an n by n diagonal matrix D and an n by n invertible matrix P. So let's underline diagonal matrix D and invertible matrix P such that A is equal to P inverse, or D is equal to P inverse A times P. A is the matrix that we want to diagonalize, and D is our diagonal matrix. So we can say that P is a similarity matrix that diagonalizes A, And likewise, D is a diagonal matrix similar to A. That means that D and A are going to have the same eigenvalues. When we diagonalize a matrix, we need to find our matrix P and our matrix D. Let's go over a procedure to find P and D. We'll start by looking at the structure of both P and D. P is an invertible n by n matrix with linearly independent columns. So we'll let P be equal to V1, V2. These are the vectors making up the columns of P, all the way up through Vn. And remember, the n is associated with the A. A is our n by n matrix. We'll make a note that V sub I cannot equal 0. And we'll see why in just a few minutes. Now let's look at the structure of D. D is a diagonal matrix that looks like this. C1 all the way down to 0, all the way over to 0, and then along the diagonal is C2 all the way down through Cn. On the next page, we'll find our vectors v and our constants or scalars c. To find vi and ci, we'll begin by writing our matrix A, the matrix we want to diagonalize, as A is equal to P, D, P inverse. Multiplying on the right by P, we get AP is equal to P times D. Now we'll plug in what P is. I've already done that on the left. Let's do that on the right. And in fact, on the right, we can plug in both P and D. So our P is our V1, V2, all the way up through Vn. And our D is our diagonal matrix C1 all the way to Cn. And then 0 elsewhere. Now we're going to multiply everything through. If we pull our matrix A in, our matrix A is going to multiply all of those vectors. Our right-hand side now looks like this. We have C1, V1, C2, V2, all the way up through Cn, Vn. Now we're going to equate the columns. Our first column is AV1 on the left, and it's going to equal C1, V1 on the right, all the way up through our last column. AVN on the left is equal to our last column, CNVN on the right. Notice that these equations are the equations for eigenvectors. So that tells us that V sub I is an eigenvector of A, and C sub I is the corresponding eigenvalue of A. Let's summarize this so that we'll have something to refer back to. Our P is equal to V1, V2, all the way up through Vn, and A is an n by n matrix. Let's just write that over here. So A is n by n. And then D, instead of written with our C's, we're going to substitute that our C's are equal to our lambdas, and we're going to get lambda 1, lambda 2, all the way down to lambda n, and then 0 elsewhere. So D contains our corresponding eigenvalues of A. We have two more little tidbits of theory, and then we'll go do an example. We say that A will be diagonalizable if it has n linearly independent eigenvectors or n distinct eigenvalues. So if we end up with n linearly independent eigenvectors or n distinct eigenvalues, we know that A is going to be diagonalizable. To determine if A has n linearly independent eigenvectors, we have to find a basis for each eigenvalue and count the total number of vectors obtained. So let's just write that as and count the vectors. We're now going to do a really important example where we're going to find a matrix P that diagonalizes a given matrix A, and we're also going to find D. Often when you diagonalize a matrix, that's exactly what you're doing. You're having to find P and you're having to find D. Our first step is to find the eigenvalues and construct D. To find the eigenvalues, we're going to solve determinant A minus lambda I is equal to 0. To find the eigenvectors, we're going to take A minus lambda I, augment it with 0, and put it in reduced echelon form. And that will enable us to find V. Let's begin with step 1. We take the determinant of A minus lambda I, so this is 3 minus lambda, minus 2, 1, and then minus lambda, set that equal to 0. So this gives us 3 minus lambda times minus lambda minus a negative 2, so that's plus 2 is 0. We multiply everything through, so we have a lambda squared minus 3 lambda, and then we have a plus 2 is equal to 0. We're going to factor that, so this is lambda minus 2. Lambda minus 1 is 0, and that gives us lambda is equal to 2, and lambda is equal to 1. I always tell students, once you find the eigenvalues, go ahead and construct D, so you don't have to go back and rethink about it when you get to the end of the problem. So our D is going to look like this, 2, 0, 0, 1. Students always ask, does it matter which one goes in which column? And the answer is no. You can put the eigenvalues in any column that you want. However, it's super important when we find P that the eigenvalues and the corresponding eigenvectors have to be in the same column. Let's now complete our second step. This gets a little lengthy. What we're going to do is we're going to find the eigenvectors corresponding to each eigenvalue. So we have to do this twice. So let's start with lambda is equal to 2. And we're going to take A minus lambda I, augment it with 0. And this is going to give us, you know what? Let's write down our A again down here so that we can see it. So our A is equal to 3 minus 2, 1, 0. There we go. Now we can refer back to that. So we're going to subtract off 2 off the main diagonal. So 3 minus 2 is 1. So we have a 1, 1, minus 2. 0 minus 2 is minus 2. And then you can see that our second row is a multiple of our first row. So this reduces very nicely. And this is going to give us V1 is equal to minus V2. And then V2 is our free variable. So our vector V, our eigenvector, is going to be minus 1, 1, V2. And we get to choose a value for V2. I'm just going to choose it equal to B1. So our eigenvector is going to equal minus 1, 1. Let's notice the 2 is in the first column. So let's write down what P is. So our first column is going to contain the eigenvector minus 1, 1. We then do the same thing for lambda is equal to 1. Our A minus lambda I augmented with 0. We're going to subtract 1 off the main diagonal. There's our A, so 3 minus 1 is 2, 1 minus 2, and then 0 minus 1 is minus 1. We're going to augment this with 0. And we have repeating rows, so we can easily reduce this. Let's divide the top row by 2. So we have a 1 and a half, 0, 0. So we end up with V1 is minus 1 half V2, and V2 is our free variable. So we can say that our V is equal to minus 1 half 1 V2. We can choose a value for V2. Fractions are usually more messy, so let's choose V2 to be equal to 2, or you could pick it to be negative 2 if you don't want a negative in the first entry. I'm just going to choose it equal to 2, so our eigenvector is equal to, we're kind of running out of space, it's equal to minus 1, 2. So let's take that and let's put that in here for P. So we have successfully diagonalized our matrix A because we found a diagonal matrix D and our corresponding matrix P. Okay, we made it to the last topic. So our last topic is complex eigenvalues and eigenvectors. We'll begin by learning a little bit about complex matrices. Complex matrices are matrices whose entries may either be real numbers or complex numbers or a combination of real and complex numbers. Let's note that a real matrix is a complex matrix whose entries have 0 imaginary part. Let's look at a typical complex matrix example where we get to learn a little bit about complex matrix arithmetic. In this example, we're asked to find what we call A bar, which is the conjugate of A, and then we're asked to find the real part of A and the imaginary part of A. The conjugate of A looks like this. What we're going to do is we're going to take the conjugate of each of those 4 entries. So the conjugate of 1 plus I is 1 minus I. The conjugate of minus I is I. 4 stays as it is. And then the conjugate of 6 minus 2I is 6 plus 2I. And the real part of A, what we're really doing when we talk about the real and imaginary parts is we're just splitting our matrix apart into 2 pieces. So think of our A as equal to our real part of A plus I times our imaginary part of A. So our real part of A is going to be 1, 4, 0, 6. For our imaginary part of A, we're going to pick up the constants that are multiplying the i's. So that's going to be a 1, minus 1, a 0, and a minus 2. Before we do an example where we find complex eigenvalues and eigenvectors, let's note that if a real matrix has complex eigenvalues, the eigenvalues and their corresponding eigenvectors occur in conjugate pairs. This is great news because it's going to cut our work in half, because once we find one eigenvalue, we can find the other eigenvalue. Same thing with the eigenvectors. In this example, we're asked to find the eigenvalues and eigenvectors of A, and those eigenvalues and eigenvectors are going to end up being complex. To find the eigenvalues, we're going to begin with determinant A minus lambda I is equal to 0. This gives us 2 minus lambda minus 3, 3, and another 2 minus lambda is equal to 0. We'll multiply this out. This is 2 minus lambda times 2 minus lambda minus a negative 3 times a 3. So that gives us a plus 9 is equal to 0. Let's write this as 2 minus lambda squared plus 9 is equal to 0. Let's move the 9 to the right-hand side. If we take the square root of both sides, we get 2 minus lambda is equal to the plus or minus square root of minus 9. Let's remind ourselves that the square root of minus 1 is I. So this is plus or minus 3i. This is going to give us lambda is equal to 2 plus or minus 3i. Alternatively, you could multiply this out and you could use the quadratic formula. I think that might be a little bit harder, but you will get the same answer. So we have our eigenvalues. Now we have to find our eigenvectors. Hang with me. This won't take too long. So let's write down lambda is equal to 2 plus 3i. And remember, once we find the eigenvector for this one, our other eigenvector is just going to be the complex conjugate, and we won't have to do any work. We'll begin with a minus lambda I, augment that with 0. So this gives us, oh, we lost a. There's a. So we have 2 minus 2 plus 3i, and then 3, and then a minus 3, and then 2 minus 2 plus 3i. Now we can move our page up. Let's simplify this. So this gives us a minus 3i, a 3, a minus 3, and a minus 3i. Just to make things easier, let's divide row 1 and row 2 by minus 3. This is going to give us an I, a minus 1, and then a 1. Again, we're dividing by minus 3, and we get an I. Now the easiest thing to do would be to switch row 1 and row 2. So let's do that. So this gives us a 1 and an I, and a 0, and then an I minus 1 and 0. We'll work off this pivot, and then we have to get the I to be a 0. So we're going to multiply row 1 by minus I and add it to row 2. So row 2 is going to be replaced with minus I row 1 plus row 2. I'm going through these steps carefully because when I did this type of problem with my students, the complex arithmetic was really hard. So we have a 1, I, 0. We're multiplying the top row by minus I, so that gives us a 0. And then an I times an I is a minus 1, and we take the negative of that, which is 1. 1 minus 1 is 0. Great. So this tells us that V1 is equal to minus I V2. So our V is given by V1 V2. So this becomes a minus I and a 1 times V2. So our eigenvector is equal to, if we choose V2 just to be 1, our eigenvector is equal to minus I, 1. And then for lambda is equal to 2 minus 3i, our eigenvector is going to be the complex conjugate. So that is going to equal I1. For the complex conjugate, you change the sign in front of the I. So our minus I became an I. We did it. We made it to the end. You may want to check out the next video in this series. It's the last video in the series, and it's on orthogonality.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.